This is what we did last time. We were looking for a common source amplifier, and we say if it is driven by a fixed current source biasing, then for each transistor there is a equivalent noise current source IN square, and since this is IN square, the impedance seen at this node is the RO of this, parallel of RO of this, but since I is the good current source with RO infinite, so this only RO of this will appear. So we say it is IN square time RO1 square is the V out noise square term will appear, and we know this term, we already figured it out, it is 4 kT 2/3 GM into RO1 square. This is what we calculated last time. Please remember it has a unit of volt square per hertz, or if you take under root of that as a noise voltage, then it is volt per root hertz. Okay. And many a time this number may come in -9 or minus kind of thing, so it's normally expressed in nanovolt per root hertz. Okay. It's not necessarily, values may be differing, and so don't say, oh, it came in pico or it came in milli, it may come in even ohms. Okay. I mean in the volts, so please don't take it, but generally noises of the order of nanovolt per root hertz. So this is what we did last time. So the noise here we assumed everywhere was essentially because of the randomness of the nature, and we say it is thermal noise. Okay, so we say it is, but as we discussed in the first few slides, there are other noise factors. This was done last time. This is just to recapitulate where we were. Another noise of interest which you have to worry about is called 1/f noise, popularly known as flicker noise. Okay. Most believe that this noise is due to random carrier trapping at interface states. This most word is very important because some others do not. Okay, so obviously I had to say most. But many of them feel that this is good enough explanation to get whatever value one monitors. Okay, so this is not a very absurd thinking. But there are many other devices where there are no interface states. So then how do you say that if there are no interface states, so why there is 1/f noise? So obviously it is not the only reason. Okay. But in MOS transistors, probably interface is so strong between silicon and silicon dioxide or any insulator and substrate, and the interface states are large numbers. In fact, those who know something about devices now, at least MOS device course or MOS technology course, the typical order may be order of 4 or 5 10 to the power 10 per centimeter square. This is the lowest one gets, 2 at best. Normally it may even go to 11, 10 to the power 11 per centimeter square. So it's very large numbers are seen actually. And they may actually carrier trapping can occur because carriers are moving at the surface. Channel is at the interface in the silicon. So trapping is very strong actually. Now this noise, because of its randomness in trapping, one say there is a noise associated, and this noise was said to be called, has shown a nature that it decreases with frequency and linearly goes down. So we say it is 1/f noise. Now if you are noted down, maybe I'll move this. As usual, we can model this as either voltage source or a current source, whichever way you feel like. We know V is IR, so whichever way you wish, you can always this, or V into G is I, either way. Okay. Is that okay? Move. In general, as I say, we can noise voltage or noise currents. It can be monitored as 1/f noise voltage is K upon C of W by L into 1/f, and if you look at currents, then K upon C of W into GM square by into 1/f. Now K is some kind of a technology constant related to a MOS technology you work with, and therefore different in different technology nodes. Okay. Cox is the oxide capacitance per unit area. W is the width of the channel, L is the length of the channel, and 1/f is the frequency. And since for a given current biasing everything rest remains constant, you can see the current noise source is proportional to 1/f. However, if you are looking for spectral density, you must integrate it because that is always used per something. So now integrate on f1 to f2 df by f. And since this gives you some df by, so here is another way of expressing this, which is I intentionally brought. You can also represent it in a different form. That was a voltage GM form. This can be written in IDS form. You know, do 2 beta IDS is equal to GM square. Is that clear? So adjust the terms. Okay. Then this K will not be same. Take some term in the K and then new constant can be given. Okay. Because that W will then cancel and L square will appear. So this is how new expression can be derived. Why I am deriving it will soon be obvious to you. So now for a given IDS biasing, one then can immediately evaluate. Instead of finding GM, one knows this is the current, so we know what is the noise associated from this. This is the method one uses often in actual designs. Okay, so I just wanted to tell you that some books or some papers, if you see, they may be using this expression rather than these expressions. They are identical. Okay, remember these K's are not same. They are, some constants have been picked up there in K plus some into something. A new name has been given. Now if I integrate this term, which is df by f term is only frequency term there, so it is log f, and therefore I can say it can be k1 by L square IDS by Cox ln f2 by f1. If you look at, take some more constant out of that, what is the constant I am taking? 2.303 also if I took out, then k2 by L square IDS by Cox log f2 by f1. So what is it trying to tell? Why this expression has been shown? If you see the spectral density for this, it shows essentially telling that the larger the bandwidth, okay, larger is the noise. Okay, is that clear? So that is something you have to understand, that there is some relationship we are looking at noise with the bandwidth. Is that clear? So when I am defining bandwidth for my amplifiers or my circuit, please remember it also influences your noise voltages, or at the end we say signal to noise ratio may deteriorate. Okay, this is something which obviously not known earlier, but now you can see that there is a dependency coming from here. We also know there is a thermal noise. So if you really want to say that two noises are simultaneously occurring, you can see this is constant, there is no frequency term here. Okay, so if you see this noise volt currents, somewhere this value will become equal to the noise voltage due to current noise due to 1 upon f noise. Is that point clear? 1 upon f noise is decreasing, and let's say thermal noise is much at, maybe I'll show you figure first and then come back. The 1 upon f noise starts decreasing as frequency increases, and thermal noise is, you can always tell that this is essentially not here only, it is like this, but it is constant. So above this value, where the 1 upon f noise has same value as thermal noise, the 1 upon f noise will continue to decrease, and therefore thermal noise will start dominating beyond this called corner frequency of noise, which is Fc. At that frequency onward, thermal noise will dominate. Below that, 1 upon f noise may dominate. Is that clear to you? So this frequency is very relevant for us. At what frequency we are operating will decide whether to use one of them. Somewhere here both are equivalent terms, and therefore normally you may put two terms all the time. If one is smaller, it will take care, the second term will mask the other anyway in numerical numbers. So for us we need not worry too much, but if you know jolly well you are working at these frequencies, I mean one need not worry too much about 1 upon f noises. But then a priori you should know for given technology node what is the Fc for you. To know Fc's you need some constants to be known, that is K's. So it has been found for example, okay, this is essentially for 0.25 micron technology. Whereas the K value which I got from the Razavi's book is essentially for 90 nanometer process. So obviously one can see why this is different in different cases. Why I said? Because as technology scales, interface properties are getting difficult, or in some cases even better. Either way, there are different technologies. Like if I put high K, I'll be worst in that. If I put silicon dioxide, I'll be much better now actually. But as we scale down, we may have to shift to hafnium oxide, hafnium oxynitride, or zirconium oxides, or as we are working at lanthanum oxides or europium oxides, very large numbers. So there, as you scale down, the K is becoming, you can see, larger and larger. What does that mean? That means noise will become higher and higher as you scale down. Is that point clear? So worry started now as we went down below 0.13 or 0.18 micron technologies. We figured out the first hit was our noise itself, because it was just increasing and increasing as the nodes start going down. Okay. You can also see the term L square in the denominator there. Is that clear? So smaller the channel length you use, larger is the noise you create. Is that clear to you? So some issue has to be understood, that why now I am talking so much about it, because you have already gone to 22 nanometer process. Maybe soon 16 will come and 11 may come and 0 will come. But the point is that the noise will start then, such a dominance that signal is not there, only noise is there. Okay. It may happen. So let's see what is the situation where this may occur or may not occur. So elevation is one way of trying to reduce. As long as we get signal to noise ratio higher, it's fair enough. Only noise increase, then you have a worry. Is that correct? So somehow we must try. So some filtering has to be done such that some way this number can be controlled. Okay, that's something we'll do later. So is this constant values of varying, you understood why they are different, because at different nodes the interface states are not same, and therefore and the channel lengths are different. So obviously the constants are, and the total noise also is different at different nodes. So as we now move towards this FC calculations, we equate these two currents or noise voltages as per whatever it is. This is noise voltage I am now taking. 4 kT 2/3 GM is equal to, okay, this is square currents only. And then we get a term which gives me kgm FC. Put F is equal to FC and solve this equation. What is it trying to say? That again you can see it is function of W and L, or L square as the, if you take IDS term, K. So larger the K, larger is FC. Is that clear? So the 1 upon F noise will start dominating if your K is larger. You can see smaller the channel length, again the FCs are higher and higher. So now 1 upon F noise is now seen even in RF circuits. Is that point clear? Everyone asks us, oh, we are talking of gigahertz, so what's the problem of 1 upon F? You can see numbers is now going towards as many as gigahertz in some cases. Normally it will be order of 100 kilohertz to few megahertz. FC is typically at the order of few kilohertz. Also it will be different for P channel and N channel device. P channel will have lower FC, N channel will have higher FCs. Okay. This also an issue which you must appreciate. Okay, the GM square term is coming because of the resistance which is coming. Resistance of a transistor is seen from the lower side is only 1 upon GM. So resistance, current is something by 1 upon GM means GM goes above. 4 kT by R is the current source. R is 1 upon GM, and R square, if you do it, is GM square. Is that clear to you? Thoda same method. So in nutshell about this 1 upon F or whatever it is, I said already, I repeat, K1 values are larger for NMOS compared to PMOS. FC for the NMOS is larger than that for PMOS. FC is a proportional to 1 upon L square. FC increases with technology scaling. Finally, FC is also proportional to 1 upon GM by IDS, which gives some understanding that if you have a larger GM, your FC goes down. Okay, larger GM. But larger GM has other problem. What is larger GM problem? Let's say I hold GM larger, then I'll proportionality will increase IDS because I'll maintain GM by IDS. Larger IDS means what? Power dissipation. So the first hit I got is I saw that, oh, I reduced power, but I hit on my power dissipation, which was decided only by earlier by slew rate, the net current available to you at the ISS for DFAMS, and it is also decided to some extent by the heat sinking possibility in the device. Okay, so the power, if some way was not connected to noise, then now we realize that yeah, power has some relationship with noise. Lower noise can be obtained if you have a larger power dissipation. Is that clear to you? So this is another feature which has now been added in analog design, that the current, you cannot just do something you like. If you do something better for X, you can see you want to maintain bandwidth, let's say 1 upon RC. If you increase C, to keep this you will have to decrease R by same amount. R in our case is 1 upon Gn. So in some way you always find that you will hurt to the power immediately as soon as you go to the real device. Is that point clear to you? This is an issue which normally many books are not telling earlier, because this was in 5 micron to 1 micron or 0.8 or even 0.18. People thought this everything is okay, manageable. Now this manageable is now becoming unmanageable. So please remember, the issues in 2010 or 12 are different from what 2000 we had. So in my earlier first course in 98, I would not have told you anything this, because I myself may not be aware of this. But as I started teaching ahead, I realized things are happening now, much more stronger worries are started than what was happening in many years ago. So please, you have a more problems than what we had. When I started, my master thesis was on TTL. TTL was that time very interesting logic, and it was very nice to work on TTLs. If I now say TTL, so some may ask what is TTL. Okay, so hopefully it may not, but so things have changed over the years. Coming back to quickly on this noise in amplifier, I'll do quickly few cases. Let's say if I have a resistive RL as the load, biasing is otherwise done, then there will be two thermal noise sources, two sources across the two components. One is due to the RL and the other is due to the transistor itself. Okay. So to calculate the output voltage, that is the noise output voltage, what is the method we apply? Use superpositions. Take one noise source, find output. Take second noise source, find output. Okay. Or to say sum them out and then actually figure it out. So for this, we all know that this transistor has 4 kT 2/3 GM. This is, what is this? This is 1 upon F noise term, and this term 4 kT by RL is RL term, and multiplied by what is the load here? RL. RL parallel RO is RL. So RL, assuming RL is much smaller than RO, so RL square. This is I square. Please remember, this is I square multiplied by RL square. So you can say I1 square R1 this, I2 square RL square is the net output voltage at the noise you will get. Okay. Substitute this.